Welcome back to Survey of Engineering. In our chemical engineering unit, we are about to go ahead and calibrate our spectrophotometers. So in this presentation, in this video, we're going to talk about how to do that. So here are your portfolio questions for this video. Number one, what is the definition of transmittance? We talked a little bit about it in the last video. We're going to define it both in words and as an equation in this video. Number two, what is the Beer-Lambert law and what do each of the variables represent? So what is transmittance? So we have our sample of something that we're wanting to measure the concentration of, and we have a light coming in from the left and some is being absorbed by the sample, and then there's some light coming out. So the transmittance is defined as the fraction of the light that's coming in that's transmitted through the sample. So we've got the intensity of light, I0, coming into our sample. Some gets absorbed and some gets refracted, and the intensity of light that is let through that sample is I. So we can define it mathematically as transmittance is equal to I, or the intensity of light coming out of the sample, over I0, the intensity of light that goes into the sample. So we have some in our little spectrophotometers that you've built. We have a light that's shining through our sample, and we have a sensor that is sensing the light coming out of our sample, and it's giving us a resistance measurement. So we're measuring R, or resistance. How is it that we need, what can we do to get transmittance, or T? So going from resistance to transmittance, this is how we do it. So you did 2 samples where we had pure water, and we assume that that is 100% transmittance, that all the light that comes into the sample goes through and goes into the sensor. So we assume that T is equal to 1 in that case. And the resistance that you measured for that sample, that clear sample, we're going to call R1. Now when the sample was black, we assume that that means that no light is coming through the sample, so the transmittance is 0. And we're going to call the resistance that you measured for that case R0. Now we understand that for the range of values that we're using for our photoresistor, the transmittance versus the resistance is a linear function, so we can write it like a line and say that T is equal to M, or slope, times R plus B, which is the intercept. So that's just our typical slope-intercept form for a line that you should be familiar with. Now we need to figure out what M and B are so that we can do our calculations and use this equation to calculate T from a given R. So we start by calculating M, or slope. And because we know 2 points, we have 2 points that we've measured. When transmittance is 1 and when transmittance is 0, we can solve for M. So we just plug in, we're going to solve for M equal to T sub 1 minus T sub 0 over R1 minus R0. That's just a simple 2-point slope calculation. So if we plug in for the known values of T that we have, we get 1 minus 0 over R1 minus R0, which just gives us a slope of 1 over R1 minus R0. We know R1 and R0 because we measured those. Now we need to go and calculate B, and we're going to use the point that we measured on the line where we had a black sample, just because it's easier for calculations to use a T equals 0. So we substitute in for T 0, and we substitute in for R0, that known value. And we're going to sub in our slope that we just figured out and rearrange, and we get that the intercept B is equal to minus R0 over R1 minus R0. Now we can plug that all back into our equation for t, now that we have known values of slope and intercept. And there's our slope that we plugged in from what we calculated before, and our intercept that we plugged in. Now we see that the denominator is the same on each of those fractions, so we can go ahead and rearrange. And we get a final equation of transmittance is equal to resistance minus R0 over R1 minus R0. And this is the equation that we're going to use to calculate any transmittance from a resistance that we measure from our spectrophotometer. Now, really what we're concerned about and what we'd like to use our spectrophotometer to do is measure concentration. So we have one more step to get to concentration. We need to understand how transmittance is related to concentration. And for the range of values that we're using, something called the Beer-Lambert law applies, which tells us that the negative log of intensity over I naught, or the negative log of transmittance as we know it's defined, is equal to some constant epsilon times C times W. So here's what each of those terms are. And this is what the Beer-Lambert law is. So C is equal to concentration, and the units are moles per liter. And for our purposes, this is going to be the concentration of our algae in our sample that we want to know. W is the width of the cuvette that we're using, and it's in units of centimeters. For our cuvette, it's 1 centimeter. And epsilon is something called the molar extinction coefficient. And it's just a constant that is specific to the type of stuff that we're measuring, the molecules that we're measuring, and the light that we're using, the wavelength of light that we're using. So it's going to be very specific to our algae and the wavelength of red light that we're using, and even to your own very spectrophotometer, because all of the spectrophotometers that are going to be built by the teams will be a little bit different. And it has units of liters per mole times centimeter, just to make everything cancel out and make that part of the equation unitless. Now, moles might be something that you're not familiar with. What is a mole? So a mole is basically just a measure of the number of things that you have. Usually it's atoms or molecules or cells or whatever smallest unit of something that you have. So 1 mole of something has 6.022 times 10 to the 23rd of that thing. So a couple of examples are 1 mole of carbon atoms is equal to 6.022 times 10 to the 23 carbon atoms. Same thing for a mole of water. It's that number of water molecules. We can go so far as to say if we had 1 mole of elephants, we would have 6.022 times 10 to the 23 elephants. And moles are just convenient to talk about a quantity of something when there are things like atoms or molecules or cells that are really small, and we'd have to talk about really big numbers if we were talking about atoms. So we talk about moles instead. Okay, so here's our procedure that we're going to do to calculate epsilon. That's what we're trying to find to calibrate our spectrophotometer. So first we're going to calculate T from R using that equation that we derived. We're going to take the minus log of it and calculate T, and then we're going to plot that minus log T for each concentration that we measure. Then we will fit a line with an intercept of 0, because when we have 0 concentration, we should have a minus log of T equal to 0, since transmittance would be 0. So we fit that line, and we're going to calculate the slope of that line, or have Excel calculate the slope of that line. And we know based on our equation that the slope is equal to epsilon times W. And since W is just 1 centimeter, the slope is essentially epsilon. So once we've calculated that slope, we have our epsilon, and now our spectrophotometer is calculated, and we'll be able to use it to figure out concentrations of our samples as we're growing algae in our photobioreactors. So at this point, I'm going to go through an Excel example of how exactly we're going to do this. So if you can see, I've set up this Excel spreadsheet, and I've entered in some value that I would have measured with a black sample for R0 and some value that I've measured for a clear sample with R1. And I have my concentration of the highest concentration of the algae that I've calculated in moles per liter. And if you looked on the cuvettes, we had some fraction of the full concentration, so we had some dilution. So we're going to go ahead and calculate exactly what the concentration is for those fraction cuvettes. And so if I have a fraction of 0.1, that means I have a 10% dilution. I can say that my concentration of that sample is equal to the full concentration times this 0.1, or 10%. And there's my calculation for concentration there. Now I can copy this formula down, since for a fraction of 0.2 or a 20% dilution, it's going to be the same formula. So rather than having to write that formula a bunch of times, I'm just going to copy it down. And I don't want this cell to change, so I'll use a little trick by putting $signs in front of the column and the row identifier for that cell, so that that stays the same as I copy down my formula. So I'm going to go ahead and copy that down, and it does this calculation of all of the concentrations for me. So here I've input the resistance that would have been measured during calibration for each of these concentrations. And now I can go ahead and calculate the transmittance based on that formula that we used, or that we derived. So transmittance is equal to R minus R0 divided by R1 minus R0. Now again, I want this R1 and R0 value to stay the same as I copy my formula down. So I'm going to use the $signs to make that stay the same. And there I have a transmittance calculated, and I'm going to copy that down. And now I can go ahead and calculate a minus log of the transmittance. So I'm going to use an Excel formula for this, and go ahead and say equal log of, and it recognizes that as an Excel formula, so log of t, and I'll copy that down as well. So now I have my minus log of t. And since I'd already set up this graph to pull data from my spreadsheet, it's showing me a plot of concentration in moles per liter. That's right here. So if I click on that, it'll show you what data it's pulling. So concentration in moles per liter versus minus log of t. And I've put in a formula here to calculate the slope of that line, setting my intercept equal to 0. So right there, we have our epsilon. So you'll have this bare bones spreadsheet without the values entered in available to you, so that you can do these same calculations. And so that's how you calculate epsilon, and now your spectrophotometer is calculated, and we'll be able to use it to determine our concentrations in our photobioreactor. So we will see you on class next time.